Okay, so we have projectile motion. Now that we're into motion in 2 and 3 dimensions, we need to cover this is you need to cover this. This is one of the sort of cornerstones of what you learn in pretty much any physics class. This is one of the big ones. Here, there we go. So projectile motion, it's a powerful tool to predict where something will land as you launch it with some velocity. It could be either ranging from a cannon, firing a cannonball, or a stunts person jumping something from ramp to ramp, or just timing how long something takes to fall off a cliff. You can determine how far it will land from the base, and it's very common in a world with constant acceleration. And that's precisely what we have. We have a Earth that provides a source of constant acceleration. Go down like that, okay. So everywhere, all the time, we have this constant acceleration downwards towards the center of the Earth. And since there's this constant acceleration, we can use those constant acceleration kinematic equations that we found in chapter 2. Even though they were for one dimension in chapter 2, in this case, we can just split them up into their two components. So you think of it as, I'm only going to think of the horizontal components, and I'm only going to think of the vertical components. So I'm just separating the two. Let me maybe make a little picture to make this more clear. So we have a graph, and it's just tracking the movement of something. This could be a projectile or a ball that you toss. Just put a ball in here. Let me zoom in a bit. So say we have a ball that we're sort of launching. It could be a, how far can you throw a baseball, or how far can you hit a golf ball? What are the components of this object, or this just projectile? Well, I can split this up into, first off, we notice this is a vector. It's got horizontal and vertical components. Let me sort of make this box that maybe we're starting to become more familiar with. This is tail to tail method, sort of one of the methods I went over when we went over vectors. But you can also do head to tail method if you'd prefer. But you see there's this vertical component right here. I'll write that after I do the arrow. And there's this horizontal component right here. So there is the vertical components, v naught y, and there is the horizontal component, v naught x. And it's safe to say that the the vertical component right here is the same as this dotted line over here, and the same with horizontal on the top. So just makes this really nice square that we can measure the sides of. Let's get rid of that. So we have just adding vectors. That's what this boils down to. We have a velocity. Say we wanted to know what this velocity at just some obscure angle, and we're going in 2 dimensions. So that will just be breaking it up into its components. the initial velocity in the x direction? Well, that's just made of, this is similar to just that vector addition example I did a while ago. So that's just the hypotenuse of this triangle times cosine theta. And in this case, it's theta naught, like that. What is the vertical component? So that's v naught y equals v naught times sine theta. Not like that. All right, so we're kind of going step by step. We're sort of building up a language of, all things can be split apart into more simple things. And those simple things are, easy to handle. This is helpful when we have, a complex problem. We just split it up into things that we already know. For, the Earth providing this constant acceleration, we need to, there's an object, projectile, it's moving. We need to know, typically the problem will tell you, the parameters of what's happening. So in a projectile problem, it'll say this object is moving this velocity at this angle and assume there's gravity, and maybe that's it. So in that case, we could say there's no horizontal acceleration, because it didn't say there was any friction or anything slowing down this projectile. So typically, unless stated otherwise, we could say if it's not accelerating, or I could say if not accelerating in the horizontal direction, in horizontal, we could say the acceleration in the horizontal direction, so a sub x is 0. And typically, it's not, all the time, it's unless stated otherwise. We'll say something, a projectile is accelerating, so is accelerating in the vertical direction. I'll just say vertical. And so saying this, assuming we're on Earth with Earth's own gravity. So the acceleration in the y, or vertical direction, is minus g. So we might have, we might have already gotten into, factoring in gravity in some of our problems on the homework. Now, what do I mean? Earlier I said, split this up into sections, components that are easy to handle. Let me do a little example of this. So we had those kinematic equations from earlier, from chapter 2. And let's do a little example of how we can, start from the base of, any problem and build up to something useful for that problem. So let's say for, this projectile, we'll say, we do this example, using one of the kinematic equations, I had split it up into a horizontal and a vertical component. So let's say, and I did write it like this, I believe, with x's on my notes. So it'd be like x equals x naught plus v naught in the x direction times time plus 1/2 the acceleration in the x direction times time squared. And we would also have, I would need to remember to also write the same exact equation for the vertical components. So I'd say y equals y naught plus v naught y times time plus 1/2 a, the acceleration of vertical times time squared. So using what we've, seen above, let's just insert these values into this equation. So for the x, horizontal components, the acceleration is 0. So that would mean this whole term right here goes to 0, and we're left with x equals x naught plus v naught x times time. Okay, so this is that equation that we've known earlier. That's displacement. So that's basically this. We know that displacement is just how fast you move times how long you are moving. And that's basically what a projectile is. As soon as you throw it, it's going to keep moving horizontally at a constant rate. So maybe next time I'll have a little video to support this. This is where I could also bring in a demo, but I don't have anything prepared at the moment. There's a constant horizontal velocity. And for the vertical component, we would put in g for the acceleration in that component. So it'd be y equals, or I could just say, I'll leave it like this. So y naught y, so velocity in the y direction minus 1/2 g t squared. So this is just one, I just picked one of the random kinematic equations, and I split it up into two separate components. I could do this with each of those kinematic equations, and given some specific measurements, that's very useful when finding something about a projectile. Let's do a little example real quick, and then I will get you guys going on the quiz. Go up here. Okay, so projectile motion example. We have, someone at graduation decides to toss their cap, and it goes, they measure at 24.5 meters per second, and they launch it at an angle of about 36.9 degrees above the horizontal. And it's caught by another student, and you can assume it's about the same height. So it's just making a little arc and ending at the same height that it started with. So what is the total time that the cap is in the air, and what is the horizontal distance that the cap has traveled? So something I like to do is just to always start with a picture so I have a clear view of what I'm trying to accomplish. So we have this sort of coordinate system, and always, it's easy to just make the initial positions 0 for anything if it doesn't give you a value already. So I'm going to make the origin right here in the center the initial position. So right when someone tosses the cap, you think that, split second when they let go, that is the origin where, x equals 0, not, initial distance in the x direction is 0, initial distance in the y is 0, and also for, completeness, it's also right when the time starts. So think, right as it is let go, 0. So it's launched at some angle upwards. So 36 degrees kind of be like that, maybe. And that is the velocity, the initial velocity, I should say. And we know that it is 36.9 above the horizontal. X, Y. That is the angle that it's launched at. First question is find the total time the cap was in the air. Let's try to make like this arc that it's going to make. Well, this vector that I've drawn, that's sort of the instantaneous velocity. So that's where it's pointed right when it starts. It doesn't mean it's going to travel this huge arc like that. It's going to taper off and go down like that. You think of this tangent line will follow that curve as it goes around the top of it. Okay, so we want to know the time, and we want to know the distance. We assume it's caught at the same height, so we could just say whenever it crosses this horizontal line again. So we have, to find the time, let's go like this. I'll say to find the time, we can start with, we know that it's going to, this is just a problem that we've kind of done already. It's just something that we're throwing up in the air, and it's going to come back down to the ground, or, up and then back down to the origin. So you time how long it goes up and comes back down to the same height. So we can use the y component, the vertical component of this kinematic equation, t minus 1/2 gt squared. And since we know it's going to start at the origin, then go up, and then come back down, and someone's going to catch it at the same height, we know that this difference in height is going to be 0. That makes our equation a lot easier. We have the rest of it still to manage. 1/2 gt squared. This turns into something with two solutions. Let me factor out a t of this equation. So v naught y minus 1/2 gt. So I'm just taking a t out, putting it outside of the parentheses. So we say that there's a solution when t equals 0. So I could just, like that, I could just divide this whole thing over, and t equals 0. But we need to remember that's right when we started the clock, and that's right over here. So initial. So it's not valuable to us. We already know we start the clock at 0. we want to know the other value. So we want to solve for this one inside of the parentheses. Doing that, we get t equals 2 v naught y over g. Okay. But what is v naught y? That is something that's not, explicitly given in the problem. We're given, velocity, but we only need the y component of velocity right here. So this is where we're, splitting a vector up into its components. So let me write down what's the y component of that vector is. So I'll say use what we already know, v naught y is, v naught sine of theta. And let's just plug that value. Let's plug this in for v naught y right here. So I'm just going to go straight to it like this. V naught sine theta over g. And I will, I'll do the whole thing. So 24.5, that's the initial speed at, that angle, or the initial velocity, times sine of 36.9 degrees over 9.8 meters per second squared. That's meters per second. So we get at the time 3 seconds after doing this calculation. Okay, the second part of the problem is find the total horizontal distance. So we want to know the time it takes to go from here over to here. And that's just a one-dimensional problem of something moving with a constant velocity. So we can actually, we can use the time value that we just found. So now that we have time, we have t. I'll say use. We can use that same exact kinematic equation that we started with up here, but we could use it for the x component. So for the horizontal components. So that one was, I'll remind you, it's the same exact thing with x's. So x minus x naught is the velocity in the x direction times time, except there's no gravity in the horizontal direction. We have to remember what that actual equation was. It was plus 1/2 acceleration in the x direction times time squared. And remember from the previous page, we saw that this goes to 0. So we have an equation that looks like this. Also, I'll say we're starting at the origin. So the initial position, the x is just 0. I'll just say x equals v naught x times t. But the same problem that we have above, what is the horizontal component of that vector? I'll just write it out in the parentheses right here, it was V naught times cosine theta times t. So that was this term right here. So doing this, we get x equals 24.5 times cosine of 36.9 degrees. You know, I should put units in here too, so that's meters per second. And times t, so that is times, all of that is times multiplied by 3.0 seconds. At the very end, we get that this person tossed their graduation cap 58.8 meters, which is insanely good for someone to toss, you know, graduation cap. You know, it's size and shape like that. But that's, you know, the basics. You know, it's projectile motion is very simple. Once you understand, you could just split it up into, you know, very simple components. It's very manageable. There are like, let's see, there were like 5 or 6 examples in the book of projectile motion, and all of them are just, you know, branching off of those previous kinematic equations, but showing you that you could split them up into horizontal and vertical components. So that's sort of an intro into their projectile motion. Maybe I'll do one more example on projectiles tomorrow, but I plan on finishing chapter 3 tomorrow and starting chapter 4 tomorrow also. So let me get the quiz. I'll get you guys started on the quiz. And yeah, are there any questions on like the notes or anything that's not the quiz right now? All right, so let's get you guys started.